Hello, good evening and welcome to the third session on tutorial session on wideband gap power device based power electronic converter design. So I'll just start in just a while. I'll just share my screen and yeah, you can just confirm if my screen is visible or not. Are you guys able to see my screen?
Yes, sir.
Okay, thanks. Okay, I'll just start. Or probably we can wait for just a minute and we will start. Okay, so I don't know. Okay, so we'll just start now. Yeah, so in this week, you guys saw about dynamic pulse testing, right? And then this week was mostly spent on fault protection. So you learned about what are the different types for preventing overcurrent faults, right? That is, you learned about the desaturation-based protection circuit. Then you learned about the DIGT-based protection circuit, SSCB, right? And then you also learned about what is called UVLO or under voltage lockout, correct? And finally, you touched upon a bit of what is crosstalk consideration, right? And how do we take care of that in the layout, right? And if you have to do a layout, there is going to be some parasitic inductances that come into picture, inductances and capacitances that appear in your circuit unintentionally, right? So you just studied a bit about that. Okay. So as usual, you'll just have a very brief, no, not exactly brief. You'll just have a spend some time on recapitulating what was learned, and then we will see the problems as usual. Okay. And so some of the slides are actually from the lecture course itself. So you would find the slides in familiar, but I just thought it would be good to brush up your whatever you learned, right? Okay, so we started with the double pulse test circuit, right? And you know that there are going to be two devices, Q1 and Q2, which are in a half bridge kind of a configuration, right? And then you have the load inductance, which is attached across the device Q1, right? There is no external load as such, like a resistive load or something. Over here, you just attach the load inductance across Q1. Okay. And what you do is you always make sure that Q1 is off. How do you make sure Q1 is off? Because the gate and source of Q1 are shorted, correct? You can see over here that the gate source of Q1 is shorted, right? That is, you're ensuring that VGS is always 0. So let me just write that over here. So over here, you know that VGS is always zero, which means that Q1 is going to be always off. Right? Q1 will always be off. Okay. So you ensure that and you connect the load inductance across Q1 and you give the pulses to Q2, right? You give the gate pulses to Q2. So over here, the device under test or DUT as we call it, DUT is basically device under test. Okay. So the DUT is the lower device or the complementary device across which load inductance is to which load inductance is attached. Correct. So the other device is Q2. So basically what happens is you want to see what happens during turn on, right? So during the first pulse, the inductor current would increase. Why is the inductor current increasing linearly? The slope of this inductor current is basically what? So this is just V equals L di over dt, correct? So the slope would directly be equal to VDC over L load. Okay. So if you know what is this time period, you will know what is this time period, right? That is, this is being fed from the pulse driver or microcontroller, right? So you know what is T1. If you know what is T1, you can find out what is the current to which it ramps up. So you will find that this current is going to be what? It is going to be 1 by L integral V dt. V is a constant DC value. So you get V by L into integral dt is just T. Or over here it is T1. So you will know what is the peak current to which it goes. Correct? If you control T1 for a given DC bus voltage, you can control what is the peak current. So you turn it off, observe what are the turn off characteristics, and then again you turn it on. You observe what are the turn on characteristics once again. Correct? So can anyone tell, like over here there are only two pulses. So instead of just two pulses, can I go on giving pulses like this continuously? Is it possible over here? Can I do this? Something like this? Continuously, can I just go on keeping feeding pulses? Anyone? Yeah. So the question is, instead of just two pulses, so over here you see that there are only two pulses, right? And that is why you're seeing that, okay, initially it increases, then you turn it off, and then again it increases, right? And then you turn it off. That's it. So this is just two pulses, right? And this T1 is going to be some microseconds, correct? A few microseconds. Now the question is, instead of just two pulses, can I go on feeding pulses, right? So let's say uh, the pulse is having 50% duty. So for zero point 0.5 period it is, or 0.5 DTS, it 0.5 TS it is turned on and 0.5 TS it is turned off. So the duty is 0.5. So can I go on keeping pulses like this to this circuit is the question, to this particular circuit. Instead of just two pulses, can I feed like that? Any guesses? Okay, so any guesses? Anandi or Lavanya, anyone? Any idea? Can we go on keeping giving pulses like this?
No, sir.
Why can't we give? You're right. Why can't we give? So what would happen? See, over here you see that this is a pure inductor, correct? And there is no external load resistor as such. See, if you take your, let's say, I will take a new slide. So let's say you take a buck converter, correct? So I will draw the buck converter in a average fashion. Okay. So this is your MOSFET 1. Okay. So this is MOSFET 2. And then what you have is an inductor and then the load. Okay. So over here, what you see is that when Q1 is turned on, right? That is, let's say this is Q1, Q2, and this is your L, and you have a load resistance R. Correct. So when Q1 is turned on, then what happens is the inductor is of course charging, but on the load side you have a load resistance that is actually taking up the power. So um, whatever power is going over here is eventually getting delivered to the load side. Correct. So that is why you tell that when Q1 is on, right? So when Q1 is on, you tell that VL, correct? If I take this as the polarity, VL is going to be VDC minus V naught. And when Q1 is off, you tell that inductor is going to freewheel, correct? You tell VL is equal to minus V naught. Okay. And this minus V naught is quite essential, right? So this would make sure that the inductor current falls, correct? So what you understand is that VL during the on time is going to be VDC minus V naught, correct? And VL during the off period is going to be just minus V naught. And you also know that you also know that um, VL is equal to L delta I by dt, correct? So during the on time, VDC minus V naught is equal to L into delta I by, during the on time we call it is dTs, correct? So you understand over here that this is a positive value, correct? So basically your di by dt is positive over here, right? Because VDC is more than V naught. Okay. So delta I or the inductor current would increase like this. Okay. And during the off period, what you observe is that minus V naught is equal to L into delta I by, and the time will be 1 minus dTs. Okay. So you understand that over here, this is a negative quantity. So this is a negative quantity. So since this is a negative quantity, your current would fall. Okay. And under steady state, this point would be the same as this point. Okay. Over one switching period in steady state. Right. So during the charging period, you have a positive voltage, and during the discharging period, most importantly, you have a negative voltage. So that negative voltage, you make sure that your delta I reduces, right? That is your inductor current is reducing. So this is your inductor current. And you know that this continues over a number of cycles. And that is why you keep on giving pulses to Q1, Q2 alternately, right? So this is what happens in a buck converter, right? So let us consider the boost converter as well. Okay, so I will draw one converter. You can tell me what kind of a converter this is. So this is the converter. Okay. So okay, so let me call this as VDC, and yeah, and then this is your V out, V naught. Okay. So what is this converter? Anyone? Can you tell what kind of a converter this is? Again, let me Q1, Q2. Or for
Boost converter.
simplicity, yeah, so this is a boost converter. So this is the same thing that I have redrawn, just we change the position of inductor. Okay, fine. You also understand that since instead of a diode, we have replaced with two MOSFETs, right? So this gives you a bidirectional operation. Um, uh, it kind of gives you a freedom, like you can have both buck operation as well as boost operation with the same converter, correct? So just we will take a very small detour. If this is a boost converter, right? So then what would you do during the on period? So Q2 is your control switch, right? So Q2 is your control switch. When Q2 is on, then so this is your L, correct? So Q2 is on, then what would happen? VL is equal to plus VDC, correct? If I take this as a polarity. And when Q2 is off, what would happen? VL would be equal to VDC minus V naught. Okay. So Q2 is your control switch. And if I want to get buck operation with the same converter, what would I do? What would I do? Just think from the reverse direction that this is your output side and this is your input side. Okay. So in buck converter, what you would do? What would you do? You make when Q1 is on, then your VL. Now the polarity for VL is different because the operation is different. The current flow direction would also be different. So this is your buck converter. Okay. So let me write it in this ink. Okay. So VL is equal to V naught minus VDC. And when Q1 is off, you understand that VL is equal to simply minus VDC. So you see that with the same converter, we are able to get both buck as well as boost operation. So this is called a bidirectional converter. Just you replace the diode with a MOSFET and you can have currents in both directions. That is, this is also possible. This is also possible. Okay. So bidirectional converter. Okay. So the point is again in boost converter, you see that during the on period, VL is equal to VDC, right? And during the off period, VL is VDC minus V naught, which means that when switch is on, so VL is equal to VDC is a positive value and VDC minus V naught would be a negative value, correct? Because in a boost converter, output voltage is more. Therefore, you will again see, you will again notice that during the positive period, your inductor current would increase, and during the negative period, your inductor current would fall. Correct? So you see that there is an equal rise and equal fall of inductor current. Correct? So this point is same as this point is same as this point. So at the start of each switching cycle, you land up at the same point. Correct? And this is what is called as inductor flux balance. Correct? Inductor flux balance, that is in steady state, or you can also tell inductor old second balance. Old second inductor old second balance. Why is it old second balance? Because V equals L di over dt, right? So V equals L V equal to L di over dt. Therefore, V into dt is equal to L into di. So you see that for a fixed value of L, right? Fixed value of L, you see that where the current starts, it is ending up at the same point after one switching cycle. So you see that this is a constant value every switching cycle, correct? So this is called whole second balance for the inductor. Okay. So now the point is, we will come back to the DPT circuit or the double pulse test circuit, right? So let me take another slide. So okay, so this was your boost converter, correct? So now we will just modify this a little bit. Now this is your, let me, so this is your boost converter, correct? And let me take a different ink and draw your DPT circuit. So if you can recall your DPT circuit, it looks something like this. And what you did was, from this point, you connected the inductor something like this. Okay, so let's name this. This is, um, let's say this is VDC, right? This is L, correct? And over here as well, this is your VDC, right? This, let's say, is input side voltage or something, right? And this is your L. So what is this only difference between the boost converter circuit and your DPT circuit? You see that over here in the DPT circuit, Vin is 0, correct? So what have you done? You connected L directly across Q1, the top device, and made sure your Vin is 0. So your Vin is 0 over here, correct? So now try to write the inductor volt second balance. Okay. So again, this is Q1 and this is Q2. So when Q1 is on, right? When Q1 is on, you see that your VL, right? I'm sorry, when Q2 is on. Okay, so when Q2 is on, right, your VL is going to be VDC, right? And when Q2 is off, what would happen? Your inductor current would freewheel through Q1, through the antiparallel diode of Q1. So during that period, there is no voltage that is appearing across the inductor. VL is 0, right? Almost 0. So what you see is VL is VDC, it's a positive value, and VL is 0, correct? VL is 0, right? So what you see is over here, LDI by dt is positive, correct? And LDI by dt is 0 over here. So what would happen to the inductor current? So if di by dt is positive, it means that the inductor current is increasing, correct? So that is why, oh, what happened? So L into di by dt is positive. So which means that here LDI by dt is 0. So if your LDI by dt is positive, it means your inductor current is increasing. So this is what happened during the on period when Q2 is on. When Q2 is off, LDI by dt is 0. So if you tell your di by dt is 0, right? If you tell your di by dt is 0, that means I is constant. Correct? So di by dt is 0, right? Therefore, what is I? I is simply a constant value, right? Because there is no rate of change. So whatever was the initial state, it will hold it, right? So inductor current reached over here, and when Q2 is off, inductor current would almost remain constant, right? And then what happened? Again, when you turn on Q2 once again, it would start rising from this value. Inductor current would start rising from this value. Okay. And then when you turn off Q2, it will remain constant. Okay, understood. Same thing we have done. When Q2 is on, VL is positive, that is LDA dt is positive. And when Q2 is off, LDA by dt is 0. Right? If your LDA by dt is 0, that is di by dt, no rate of change of current. Current does not change at all. So your current is constant. Okay. So there is an increase over here during Q2 on and flat region during Q2 off. And Q2 on, Q2 off, and so on. Right? Right. So from this, can you tell why, coming back to the original question, can we feed pulses like this to the DPT circuit? Continuous pulses? Sorry. Can you tell why, can we feed continuous pulses? I mean, why not? Why can't we feed continuous pulses to a DPT circuit? I don't know why it is going off, but yeah. Can you tell now why can't we give continuous pulses to DPT circuit? Are you understanding? Like the reason?
So the inductor current will keep on
Right.
increasing. So the device current rating, when it touches or goes beyond that device current rating, it will damage the device.
Correct. Right. So this is why you should not give continuous pulses. Right answer. Right. So just for your information, once something like this happened in our lab, right? So mistakenly we gave continuous pulses to a DBT circuit. Okay. And what happened was the inductor current went on increasing, and because of too much excessive current and excessive heating, the devices caught fire. Okay. So the board got burnt, right? So this is why you should be very careful with DPT circuit, that you can just give pulses, just 2 pulses or 3 pulses, not more than that. If you give continuous pulses, then the device is going to get damaged. Okay. It may even cause your board to catch fire, PCB to catch fire. Okay. Right. So we studied about how to do that, about DPT circuit. So this is just taken from your lecture slide, right? That is, you know how to design your load inductor. We just saw that, and then your decoupling capacitor, correct? So decoupling capacitor is something that is attached very close to your half bridge circuit. Okay, so you imagine physically what you would be having is the source, correct? So there would be a source over here, plus DC minus DC, correct? And then let's say your PCB is over here. Okay, so this is your PCB, right? And so what you would be having is in your PCB, you would be having the plus DC terminals, correct? And then there would also be the middle switching node terminal. Okay, so these are the terminals in your PCB. And what you would do is you would attach your inductor between the plus DC terminal and the midpoint, correct? So you would externally attach it, right? External to the board. Okay. And then you will be having your devices over here. So let's say this is one device and this is the bottom device. Okay, so this is your DPT circuit. So what do we have over here? This is your DC supply, correct? And then this is your PCB. So physically, you can imagine that from the plus terminal to the board, right? From the plus terminal to the board, you will be having a wire, correct? Similarly, from negative terminal to the board, you will be having a wire, right? So this is how your circuit would look like. And most probably your energy storage capacitors might be somewhere here itself. Okay, and you will be having long wires that connect from your power supply to the board. Okay, so now these wires may seem like a direct connection, direct short circuit, but if you talk in terms of very small nanoseconds or so, what you would observe is that these wires are made up of parasitic inductances. Okay, it can be a few tens or even hundreds of nanohenries. If you measure the inductance, you would see that this is a few tens of nanohenries. Okay, whereas this inductor would be a few microhenries. Okay, so you will be seeing that the wire is adding some inductance, correct? And that is what you learned from the parasitics. Parasitics itself, I mean the parasitics portion itself, that you will be unintentionally having inductances over here due to physical connection, right? So in order to bypass this inductance, what people came around or what people thought is, let us have smaller capacitors just across the half bridge, something like this. Okay, on the board itself, very small capacitors, which will make sure that you bypass these inductances. You will read more about that eventually, but yeah. So you want to have capacitors over here, which will hold the DC bus voltage, and they are very, very close to your devices. So those are called decoupling capacitors. So they basically decouple the inductances, unwanted inductances that come due to these physical connections. Okay, so these are known as decoupling capacitors. And of course, the decoupling capacitor should be rated for. So what should be the rating of decoupling capacitor? What should be the voltage rating of decoupling capacitor? Should it be, what should be the voltage rating for decoupling capacitor? Okay, so this is your VDC, correct? So your decoupling capacitor should be rated for more than VDC. Okay, or else the decoupling capacitor would fail. So you make sure that the decoupling capacitor you choose is at least 100 times your device capacitance. Okay, this is one parameter for choosing, right? And then you also have to choose your energy storage capacitor, right? Okay, so now the point is, we just saw a few slides back. Yeah, so see, so this is the device current. And we also saw that the inductor current is going to look something like this. If you take a DPT, it would look something like this. Slowly it would fall, very slowly it would fall to zero. So who would be giving the current? Who would be giving this current, right? This much current, this much current. So it should come from an energy source, right? So because you are basically over here, we just saw that there is no load in the DPT circuit. There is no load. So what is the load? The load is actually the inductor only. Okay. And if you want to feed energy to an inductive load, right? So basically over here, you're feeding energy to an inductive load. So what would be that energy? This energy is going to be, let me take a new graph or a new slide. Yeah. So we just saw that your DPT current or your inductor current would be something like this. Okay. This would fall very slowly. I have just drawn it to be faster, but if you see it, it would be even slow. So you focus on this particular curve. Okay. So over here you see that the inductor current IL is increasing from 0 to some value. Let's call this as capital IL. Okay. So your inductor current is increasing from 0 to capital IL. Correct. And in how much time? And this happens in a very short time. So very short time, as in like let's call it T1, and this would be somewhere around a few microseconds. So in a few microseconds, a huge amount of energy is being transferred to the inductor. Correct. So what is the energy transferred to the inductor? E is equal to half L into I square. Correct. So over here, what is I? I is basically half into L into I1 minus I2, right? So IL minus 0, that is half into L into IL square. So this much amount of energy is being transferred to the inductor. Okay. So now you understand that there should be a capacitive element, right, that can supply this much amount of energy to the inductor, right? Because you know that L and C are complementary elements. So you know that, so there needs to be a capacitive element which is able to supply this much amount of energy to the inductor. Correct? Okay. So this is on one hand. On the other hand, if you go back to the DPT circuit, so let me include capacitors in this circuit. So you will be having capacitor something like this across VDC. So the capacitor is expected to hold VDC amount of charge, right? Or block VDC amount of voltage. So initially, capacitor was holding VDC. Okay. Now what would happen? You have turned on Q2 and there is VDC voltage across this capacitor, and you know that when Q is turned on, the current is going to flow something like this. Correct. This is how the current flows when Q2 is turned on. So who would be giving me this current? Who would be giving me this current? It would basically be this particular capacitor. This is giving me the transient current, as we call it, right? So this increase in, so this particular phase, so this is basically coming from, oh, so this is basically coming from the capacitor, correct? Okay, so now we have to ensure that the capacitor is able to supply this much amount of energy while holding VDC. Correct? You don't want VDC to fall. Okay. So you want to have a stiff DC source over here, right? You want to have stiff DC source and you want to supply this much amount of transient current. Okay. So can you give a guess what would happen to the capacitor voltage if I have to get this much transient current? Would I be seeing any change in the capacitor voltage, or would it be same if I have to supply this current, this kind of a current to an inductor, right? Suddenly from 0, I want to raise it to IL amperes. That is, let's say 20 amperes or 30 amperes, whatever it is. So would I be seeing any change in the capacitor voltage? Any guesses?
Capacitor voltage rating must be greater than VDC.
That is correct. Capacitor voltage rating should be, yeah. So capacitor voltage rating, that is, let's call this as V cap rating, should be more than VDC. Right? Correct. So this is one. Now let's say you have told that capacitor voltage rating should be more than VDC. So let's say this capacitor is already charged to exactly VDC. Okay, you consider a different circuit. You have a capacitor which is already charged to VDC, right? There is a switch over here, and then you connect it to a load. Okay, I have connected to any load, resistor load, inductor load, whatever it may be. Okay, so you have a switch over here and you connect it to a load. The capacitor is charged to VDC, or as you may have noted, something like this, right? VC 0 minus, initial state is VDC, and at t equal to 0, you turn on the switch. Then what do you expect VC to happen? Like, what would happen to VC? Would VC be same as VDC, or would VC increase, decrease? What would happen to VC? V capacitor? What would happen to the capacitor voltage? See, initially you had a charged capacitor, right? Let's call it, we have a charged capacitor, and then we connected across the load. Suddenly I will turn on the switch. There is a load across the capacitor, charged capacitor now. So what would happen to the capacitor voltage? Would it be holding VDC, or would the capacitor voltage increase or decrease, or what would happen to capacitor voltage?
It discharge, it decrease.
Correct. So VC would decrease. It would discharge. Correct. Now apply the same principle over here. So what is happening is, so as we were talking some time back, you have the capacitor connected across as the DC bus, right? And across the capacitor, there is an inductor, right? You turned on Q2. So what would happen? Inductor current should increase, something like this. So as the inductor current increases, it means that it is, where is this current coming from? So if you analyze it, this current is coming from here, correct? So basically what is happening, this capacitor is discharging. You apply the same phenomenon, right? Just there is an inductive load, whatever be it, that is drawing some current. So what would happen if you draw current from a capacitor? If you draw current from a capacitor, capacitor voltage drops or capacitor voltage dips, correct? So initially, the energy stored in the capacitor, E initial, or let's call this E0 minus, EC0 minus. Initially, the capacitor energy was half into C into VDC square. Correct? Initially at this point. Now what happened was you kept Q2 turned on for T1 amount of time, and the inductor current increased something like this till IL. At the end of T1, right? At the end of T1, you know that the inductor current has increased. Therefore, you know that capacitor voltage has reduced, correct? So capacitor voltage, let's say VC0 minus, initially it was having VDC. Now what you can expect is, after some time, VC at T1, what would happen? VDC would have dropped. Let's say it would have dropped by some delta VDC, correct? It would have dropped by a small value. We have to design the capacitor accordingly. We have to make sure that VC doesn't go to zero, right? Whatever we do so far, we are assuming that there is a stiff DC voltage at the input. There is a fixed constant VDC, but you know that in reality, a capacitor cannot hold same amount of charge while discharging as well. Correct? It cannot hold the same amount of voltage. So if capacitor has discharged, that is, it has supplied current to the inductor, it means that the capacitor voltage has dipped by some amount. So you can understand that capacitor voltage was initially VDC, and then the capacitor voltage at T1 became VDC minus delta VDC, right? For simplicity, let's assume that the capacitor voltage is falling linearly. So capacitor voltage was VDC and it fell by delta VDC. let's assume that the fall is linear. You know that the fall is going to be 1 minus e power minus t by 2, something like that. But let's assume for simplicity that the fall is linear. Okay. So VDC, this is VDC minus delta VDC. Okay. So what do you see? EC at T1 is equal to half into C into what is the voltage? VDC minus delta VDC the whole square. Right. So this is the voltage, this is the energy spent by the capacitor, right? Energy spent by the capacitor for doing this double pulse test. So you again understand that you cannot keep on giving continuous pulses. If you keep on giving continuous pulses, eventually at some point this delta VDC will go on getting larger and the capacitor will discharge totally. You cannot have that, right? So yeah, so coming back, at this point, the energy is this, and at T1, the energy is this, right? So now you try to understand the energy expended by the capacitor within this time interval, right? Between 0 to T1 is going to be what? EC T1 minus EC 0 minus, right? So, and what is this capacitor energy happening? So, going to this capacitive energy is being transferred to the inductor. So, this is being transferred to inductor. That is, this energy is getting converted into half Li square. So that is why you would have read in resonance circuits as well that if you have LNC, what would happen? LNC are continuously oscillating. What you actually mean is that L is charging, C is discharging, C is charging, L is discharging, something like that. Complementary reaction happens, right? So similarly over here, this capacitive energy is discharging to the inductor. Okay. Do you understand till this point? Can you just give a thumbs up if you are able to get this concept? Very simple, right? Half CV square at 0 and at T1. That is the difference between the capacitive energy is getting transferred to the inductor. That's what is happening during the pulse. Okay. So are you able to understand it, both of you? Is it fine?
Yes, sir.
Yes, sir.
Okay. So now the point is, can you tell, should this energy, capacitive energy, should it be more than the inductive energy or less than inductive energy, or how should it be like? How should you design the capacitor? Now the question is, how do we design the capacitor, right? Because you know what is L, right? You will know what is IL because you want to, let's say I want to do the double pulse test at 30 amperes. I know what is IL, I know what is L, correct? And I know what is VDC. Let's say 400 volts. I know what is VDC. Now I want to design the capacitor. Okay. So you tell me, how should the capacitor be designed? Like, should the capacitive energy be more than inductive energy, or should the capacitive energy be less than inductive energy? What should be the relation for designing it? So you understand there's going to be some relation between this half CV square thing and half Li square. But how do we write the equation? Like, should the capacitive energy be more or less? Can you just
Capacity
guess?
energy could be more.
Correct. So capacitive energy should be more only then, because we don't want the capacitive energy to discharge ideally, right? We want it to maintain a stiff DC bus voltage, right? So what we do is, see, let's go to the next slide. So what we do is that we want to ensure that, as you told, delta AC should be more than EL. That is half CV square minus half C into V minus delta V square should be more than half Li square. Okay. So you fix some value for delta VDC, let's say 1% to 5%. That is, I want VDC to fall only from VDC to delta VDC, right? VDC minus delta VDC. And I want this delta VDC to be as minimal as possible. Typically, people keep between 1% to 5% of VDC. Okay. If you have stricter values for this, let's say instead of 1%, I want at 0.1%, then you know that from this relation itself, if delta VDC reduces, the capacitive requirement increases. Okay. So this is how you design the energy storage capacitor. That is, half L is half CV square. The difference between the half CV square at 0 t equal to 0 and at t equal to t1 should be more than half Li square. This ensures that the capacitor does not discharge so much, right? And at the same time, it is able to supply the required pulse current or the transient current. Okay. I hope you are able to understand this. Let's okay. So this is about the capacitor, energy storage capacitor. Okay. Okay. So then there is something called as a bleeder resistor, which is connected across the capacitor. Okay. If you see in physical circuits as well, they will connect this bleeder resistor. Okay. So now let's say you have done the DPT, right? You have completed the double pulse test, but still this DC source is connected. And then what you do is at some point you will remove the wires, right? At some point you will remove the wire. Okay. We just saw that the capacitor will maintain the entire DC bus voltage. Okay. Now that experiment and all, everything is complete and we remove the DC source. But if you do not provide any path for the capacitor to discharge, then the capacitor will hold the charge for a very long time. Okay. It will hold up the charge, right? So ideally, if you see, the capacitor should keep on holding the charge, right? But you don't want that. Like once your experiment is complete, you just want to turn it off. Like you just want the board to go into passive state once again. So then you have to have an alternate discharge path for the capacitor so that it loses all of its charge. Okay, and that is what is called bleeder resistor. So you will have a resistor across the capacitor. So that is what I was talking about earlier, that you will have, let's say you have VC of 0 minus as VDC, you connect a resistor and then it will discharge through this resistor, right? So precisely for that only we have bleeder resistors. So these bleeder resistors are just connected very near to the capacitor so that they provide a discharge path for the capacitor when necessary, when you don't want the circuit to operate. Okay. Even if you don't provide any discharge path, ideal capacitor is something like this. But practically you will be seeing that across this capacitor, there is a what is called as a leakage resistance across this capacitor. So this is due to non-idealities in capacitor manufacturing. So this can be of the order of a few mega ohms. So even if you don't have bleeder resistor, the capacitor would self-discharge. This is called self-discharging phenomena. So the capacitor would self-discharge. It would very slowly lose its charge. It's like, if I can tell you with an analogy, let's say you have a battery, right? You have a battery, you do not use the battery for a very long time. You do not use the battery at all. So then what you would see, it's even though it is looking like a new battery, nothing is working with that battery, right? And you see that the battery has already discharged, but you did not connect it anywhere in any circuit. Reason is because of this R leakage. Internally, it due to the chemistry of it, you can tell, right? Because basically, battery or even a capacitor is going to be what is known as an electrolyte. There will be a cathode stick and there will be an anode stick. So through this, there would be some discharge path. Okay. So this is something that is unintentional, but it is coming due to the material or chemical properties. So this is called a leakage resistance across the capacitor, right? So through that, the capacitor will lose its charge, but it will take a very long time, right? So anyway, this is just an extra piece of information, but the point is you have a bleeder resistor and you understand that the bleeder resistor should be rated for particular power level, and the power level will be VDC square by whatever is the resistance. So this would be the power loss through the resistor. You will see that you will get resistors rated for 5 watt, 10 watt, even 20 watt and 30 watt and so on. Okay. So the resistor should be rated for VDC and it should be mostly rated for this power level. So once you know what is your R and what is your C, you can predict what would be the time constant, right? And you of course know that beyond 5 tau, the capacitor would have totally discharged. Beyond the 5 times the time constant, the capacitor would have totally discharged. Right? Again, simple, right? That is, you have a bleeder resistor and you are just seeing how much time it takes for the breeder register to discharge. Okay. Okay, so I think we are done with DPT over here. I think I have gone into a bit of how we are designing. So I hope over here, like let's say you get any numerical problem wherein they tell that okay, VDC is 400 volts, I is 30 amperes, and L is this much microhenry. I want delta VDC to be within 1%. Then you should be able to design what is CDC. So you can get design problems over here. Okay. So I hope till this point it is clear. And yeah, of course, over here as well, you can get tau is equal to RC and something like at what time the capacitor would discharge to 99% or 98%. You know, tau is equal, I mean, the settling time is T is equal to 5 tau, something like that. Correct. So I think you will be able to do all of this. Just give me a moment. I'll just get some water and we'll just continue. Okay. So till this point, is it clear? Yeah. Do you have any doubt? Is it actually there are numerical? I mean, there are theoretical questions, but I feel that I have anyway. I have uploaded all the lecture slides in the drive link. I hope I think I gave the drive link last week itself. So let me check that. You can go through those questions from the PPT. So they are already there, but I feel that this kind of a discussion would benefit. Yeah, so this is the drive link. Okay. I feel this kind of a discussion would be helpful for you as well. Okay. Copy, do
Sir,
you have an
sir,
option?
the
Sorry?
drive link, last week drive link unable to open. Can I?
Can you go over here and check once? I think I have uploaded today. I uploaded even today's PPT and also.
Okay,
Um,
sir. I'll check once. Okay, sir.
do you have this link or like? Do you have this link?
Uh,
I'll just open it. Like I hope you are able to open it. Yeah. So I mean, all the PPTs are over here. The idea is that see, we have a lot of theoretical questions as well. But point is, theoretical questions you don't have much scope for discussion. At least if it was some numerical, I can solve and show you. Correct. So that is why I want to have this kind of a discussion where you get some intuition as well and try to understand things, right? Instead of just discussing theoretical part aspects. Correct. Okay, so just give me 2-3 minutes. I'll just have some water and then we'll just resume from probably 7:10 or 7:12. Okay. Okay, I'll just resume now. Okay, so so that was about the double pulse test. You need not remember or memorize all these formulas. Just you know how to design, right? Just half LA square should be provided by half CV square minus half CV square into half C into VDC minus whatever is the delta VDC, the whole square. Just half CV square, half LA square relation. Okay, right. Okay, so we will come to gate driving, right? So when the device turns on, right? The device requires QG amount of charge to turn on, and let's say QG amount of charge to turn off, right? That is you're basically charging and discharging the gate source capacitance. Or if you inject charge into the gate, you're trying to, if you inject charge into the gate or the gate capacitance, then the gate capacitance increases. So gate capacitance voltage increases. If your gate voltage increases beyond threshold voltage, the device turns on, and vice versa, right? So during turn on, you supply VCC amount of VCC voltage, right? And you supply QG amount of charge into the gate capacitance. And that's the energy expended, or that's the energy needed just to turn on your device. And similarly, to turn off the device, you apply negative voltage, VEE, right? And you take away QG amount of charge. So you supply QG amount of charge during the on time, you're taking away that much amount of charge, right? So by applying a negative voltage VEE. So the total EPS, or the total gate power, is going to be what? VCC minus VEE into QC. That is the summation of this plus this. Right? So once you know your energy, you know that your power is basically energy into switching frequency, or power is basically energy by time. That is the definition, right? Or in other words, you know that energy is basically P into T, power into time. Okay, so your power is basically what? P is equal to energy into the switching frequency, right? P is equal to E into Fs. So if your switching frequency is higher, you need a larger power. And where is this power coming from? This is coming from the gate driver. So this is coming from the gate driver IC. So your gate driver IC should be rated, or it should be able to supply this much amount of power. Okay, so that is why there is a limit on the switching frequency. You cannot go on increasing the switching frequency, right? Why? Because your gate driver AC may not be able to supply this much amount of power. Okay, so this is a constraint. So when you choose your gate driver AC, make sure that the gate driver AC is able to supply this much amount of power. Okay, right. So during turn on, VCC is the turn on voltage, and QG amount of charge is being pushed into the gate. During turn on, VE is the turn off gate voltage, and QG amount of charge is being extracted from the gate. So the total power is going to be the summation of these two, right? And it happens every switching cycle. So let's say you take a buck converter, correct? So you know that the device current is going to be something like this, right? So every time the device turns on, correct? So let me take a different color. So every time the device turns, oh, so every time the device turns on, every time the device turns off, this is happening. This much amount of power during turn on, and this much amount of power during turn off. Again, this much amount of power during turn on and during turn off. So every time, so during every switching frequency cycle, this is happening. That is why the switching power is going to be summation of these two energies into switching frequency. Why? Because this is repeating every switching cycle. Every time the device turns on, every time the device turns off. So that's why we multiply it with the switching frequency. Okay, right. So we studied about what are the decoupling capacitors for a power device, for the power source. That is, you have the decoupling capacitor over here. I had also mentioned that, see, you would be having something like this connecting inductance. In order to bypass this, we have decoupling capacitor, which will bypass or decouple the external parasitic inductances such as these, right? So we are having this for the power circuit, a similar decoupling capacitor, right? So this is the decoupling capacitor for the, sorry. Hi, so can you please mute yourself?
Hello.
Yeah, hi. Do you have any doubt?
No, I did it.
Okay, so in that case, I would request you to please mute yourself.
Okay.
Yeah.
Chinder juice. Yeah.
Okay. So we were just talking that there are going to be parasitic inductors like these. So due to physical connections, a similar argument is valid for gate drivers as well, right? And that is what is shown over here. You may be having the supply over here, VCC, VE supply over here, but the connecting wires, right, or the connecting traces in the PCB itself, they may have some parasitic inductances, few nanohenries, right? So what would happen during transients? There would be some LDA by dt drop across these, and you don't want that. So you will add capacitors over here to maintain a stiff voltage of VCC and VE respectively. Okay. So again, how would you design these capacitors? You would make sure that the capacitors are able to supply QG amount of charge, correct? They will supply QG amount of charge, and they should also not discharge so much, correct? So VCC is, let's say VCC is 15 volt, right? You want C1 to hold 15 volt ideally, but you know that when the capacitor discharges, voltage falls, right? So you would want the delta VCC, right? That is whatever is the dip from 15 volt to be very, very small, right? That is delta VCC should be small, correct? So this is how you design the capacitor, that C1 should be what? C1 should be supplying QG amount of charge for the gate driver, QG amount of charge to the switch, and there should not be much discharge in VCC, or there should not be much reduction in VCC because of supplying QG amount of charge. So that is delta VCC, right? Similarly, C2 as well. C2 is going to take away or extract QG amount of charge when the device turns off. And because of that, it would see a dip in VEE. So you don't want that dip to be too large, right? So I hope you understand that this is simply a capacitor relation. Q is equal to C into V. From there only we have written, right? Q is equal to C into V. Correct? Okay. Okay, so this is just the decoupling capacitor for gate driver, and I think in your lecture slides you went through a case study for Wolfspeed MOSFET, SiC MOSFET. So the breakdown voltage, rated current, gate charge is your QG, correct? And your dVdt during turn on, dVdt during turn off is given, right? Your turn on, so turn on voltage or VCC is given, VEE is given, and RG internal is also given, correct? So you saw about how to select the isolator and see how to select the power supply, gate driver IC, gate resistors, and decoupling capacitors. So are you guys okay, familiar with this, or should I go through this once more? Are you guys okay with this? Like the design of all of these, I think you went through in your lecture slides, right? Is it fine? Should I go through it once more, or I thought I can discuss about the desaturation protection? Is this fine? Have you gone through the lecture slides? That is how you select. Okay, so I will just explain very briefly. So first you have the signal isolator to kind of isolate between your microcontroller and the power device. So you will be having the microcontroller. So this is your microcontroller, and I should draw it perhaps in a better fashion. So you will be having an isolation, right? So what the isolator does, so you will be supplying your pulses from microcontroller, and microcontroller is with respect to controller ground, or we call it a signal ground. Okay, so this is called signal ground. So this is from microcontroller. So microcontroller, you will get something like this. And what signal isolator does, as you know, is it would convert it with respect to power ground, right? And you would be getting the same pulses reconstructed, but with respect to your power ground. So basically, you have isolated these grounds. So this isolation is mainly of three types commercially. So one is called transformer isolation, which we are very familiar about, correct? So you have something like this, and there will be flux linkage between both of these, and that would induce the voltage on the secondary. So this isolation can be transformer isolation. This isolation can be capacitive isolation. Okay, so you have capacitors in the forward path, you have capacitors in the return path. Okay, and there can also be optocoupler based isolation. Okay, opto isolation as we call it. This is very famous nowadays, opto isolation. Okay, so that is you will be having a photodiode, right? So what is a photodiode? When you give excitation, it emits light, right? So then on the other hand, you will be having a phototransistor. Phototransistor means it would get forward biased if light falls on the base of the BJT. Okay, so you have a photodiode on the transmitting side. So let's call this as transmitter side. And on the receiver side, you will be having a phototransistor. So on the transmitting side, you will have a photodiode. So photodiode, in what happens in a photodiode? You give voltage over here, the diode turns on, it emits light, and then the light information will fall on the phototransistor. So when the transistor turns on, you understand that there is going to be a pulse. Okay, you connect it to VGG and you will be right. So this is how opto isolation happens. So the transmission of the information is through light. Okay. Anyway, so this is just some extra piece of information. You have three isolation techniques. One is transformer based isolation, one is capacitor based isolation, and one is opto based isolation. Okay. So you know that the isolation should be able to withstand your DC bus voltage, which is 1200 volts. It should withstand the maximum dVdt. It should withstand maximum dVdt. That is, it is also known as common mode transient immunity. How much is it immune to dVdt? How much is it immune to dVdt? Okay, because there will be some capacitive coupling um, between the switching node where the dVdt happens and your signal isolator. If that is getting breached, right, that is getting breached, then what might happen is there will be a direct connection. Okay. So basically, let's say in this isolator, you will be having a parasitic capacitance. A parasitic capacitance There will be this is a parasitic. It's not a physical connection. It's a parasitic capacitance. Just there are two plates over here, or two, not even plates, just two connections. There will be some parasitic capacitance of the order of a few picofarad. And similarly over here as well, between this ground to this ground, we call them as completely isolated, but you see over here, there can be parasitic coupling. Okay. If your dV by dt is very high, then there would be a substantial amount of current that would be flowing through this path. Okay. So once there is a current established, then the isolation is breached. Correct? So you have parasitic capacitance coupling between your signal ground and your power ground. Okay. So this is your power ground. Okay. So how will you prevent this current, and what is this current? This current is simply C into dV by dt. Okay. Oh, I don't know what happened. So okay, anyway, so there is parasitic capacitance and there will be a current. This current is C into dV by dt. If the dV by dt is substantial, right? If the dV by dt is substantial, then this current becomes substantial, right? And if your current is very substantial, then what happens is basically there is a conduction path, right? So your isolation is getting breached over here, right? So this is what is called as common mode transient immunity. So how immune is your signal isolator to dV dt changes? You should choose a signal isolator that can withstand very high dV by dt. Okay, we also call this a slew rate, voltage slew rate. What is the slew rate for the signal isolator? Or what is the common mode transient immunity? It should be able to withstand a very high dV by dt. Okay, fine. Just some extra piece of information which would be good for you guys to know. Right, so we saw about the types of isolation and the parasitic capacitive coupling and how we should avoid breaching it by choosing a signal isolator that can withstand high dV/dt. Okay. Similarly, for the gate driver as well, right? So the gate drive voltage, of course, the gate drive should follow the gate drive voltage criteria. It should be able to supply whatever is the peak current, right? What is the peak current? Just V by R. So R internal is given, and you know what is VCC and VEE. So just directly P current is VCC minus VEE by R3. So these are areas where you can be asked questions. Okay, so it is good to go through these. Okay. Anyway, these slides will be uploaded, and these are just screenshots taken from your course itself. Right, and similarly, we studied for the decoupling capacitor as well. That is, the capacitor should be able to supply Qg amount of charge during turn on, and it should be able to extract Qg amount of charge during turn off. And there should be minimal delta Vc and minimal delta VEE. Over here, VCC and VEE are 20 volts and 5 volts. So VCC is 20 volts, VEE is 5 volts minus 5 volts, right? And they have considered delta VCC and delta VEE should be 1% of VCC or VEE. That is why they have multiplied delta VCC is basically 0.01 into 20. This is 0.01 into 5. Okay, 1% is what is being considered, and that's how you kind of design the decoupling capacitors. Okay, so one percent of VCC. So we have seen how do we design signal isolator, gate driver, and then of course the capacitors, right? So just you know that when you use capacitors, the capacitors are going to supply some amount of charge and hence they are going to discharge. What is the charge that they are giving, or what is the charge that is being given to the gate, and how much are they discharging? That is delta VCC. Using that, you can find out what is the capacitance. Okay. And if it is feeding a inductance, as in the case of DPT, what is the half CV square, half LA square relation? That's it. Okay. Fine. Before we go to prevention of false turn on, we will see what is under voltage lockout. Okay, so why do we need under voltage lockout? Like, you studied about UVLO, but why at all do we need it? What would happen if there is no under voltage lockout? What is the motivation behind having UVLO? Can someone tell why do we have under voltage lockout? Okay, I'll just take a new slide. See, you would have studied that. Let's take a MOSFET, right? So you have some characteristics, something like this. Right? So this is for increasing values of, so this is for increasing VGS, right? So this is VGS1, VGS2, VGS3, and so on. So you see that as, let's label properly. This is ID, this is VDS. So this is just the output characteristics. Output characteristics. And you also know that generally we operate the MOSFET as a switch, right? So as a switch means you operate it in cutoff region, or you operate it in the linear region till this point. Correct? So where the characteristic is kind of linear, right? That is, you have a linear increase. You have a linear increase over it. You have a linear increase. You will have a linear increase. So this is where you operate the MOSFET. So now you see over here, for different values of VGS, you are having different slope, right? The slope is different in all of these cases. And what is happening for VGS more than VGS3? Yeah, VGS3 more than VGS2, more than VGS1. You see that in each of these cases, slope is more, right? So what is the slope? Slope is basically delta ID by delta VDS, right? The slope is more, or slope is basically 1 by R, right? So 1 by R is more, correct? Or slope 3 more than slope 2 more than slope 1, correct? So if you tell slope 3 is more, it is 1 by R, therefore R3 less than R2 less than R1. Inequality changes because it is 1 by R. So you see that the on-state resistance, right? On-state resistance is lesser for VGS3, and okay, and then it is less. It is less for VGS3, less than VGS2, less than VGS1. Correct. So you see that at higher values of gate source voltage, at higher values of VGS, you see that RDS is lesser. RDS is lesser. So if your RDS is lesser, what would happen? Then your I into R drop is lesser. Therefore, your I square, oh, therefore your I square R ohmic loss. Ohmic loss is going to be lesser, right? So that is why you always want to operate at higher values of gate source voltage, right? Because so that you get lower RDS value, lower on-state drop and ohmic loss, right? Now the point is, the threshold voltage for the device, maybe let's say threshold voltage is somewhere around 3 volts, but still we see that VCC value is somewhere around 20 volts, right? The reason is this only. If you can also operate at 3 volts, no problem. But the point is at 3 volts, the device is just turned on and the RDS is very, very high. You don't want to operate over there. You want to operate at a high gate source voltage so that your drop is lesser. Okay. Now the point is in under voltage lockout, right? So what would happen is it would be sensing the gate source voltage. Okay. Gate source voltage, right? So let's say that let's take some numbers for our own convenience. So let's say this is let's say this is 4 volts, right? Let's say this is 8 volts. Let's say this is 12 volts, and let's say this is 20 volts. Correct. Okay. So now the point is, you see, if you're operating at 20 volts, the RDS is very, very low. If you operate at 12 volts, the RDS is bit higher. If you operate at 8 volts, the RDS is very, very high. So you don't want to come at 8 volts. You always want to remain over here or remain over here. Something like this, right? So that is why in under voltage lockout, if it senses that the gate source voltage has gone below VGS3 for some reason, you want the gate source voltage to be at 20 volts, ideally during on state. But if it senses that the gate source voltage has gone below VGS3, then it would turn off the device, because or else the device will start operating at with a very high ohmic loss. Therefore, heating will happen and the device might fail. Okay. So that is why what the purpose of ULO is, if it senses an under voltage in the gate source, then it will turn off the device. Okay. Did you understand? This is what is called as under voltage lockout. So did you understand what is UVLO? We don't want the, yeah, did you understand? I'm not able to hear you. So you can just give a thumbs up if you understood, or if you have any doubt, you can just try. I'm not able to hear you, sorry. Yeah. So this is called UVLO, that is, I'm not able to hear you. No worries. So this is called UVLO, wherein you ensure that the gate source voltage doesn't fall below a particular value, and or else the device may heat up, right? Okay. So if this is fine, we will go into what is called DSAT protection, right? It's a very, very widely used protection scheme for SiC MOSFETs and IGBTs, and we will see how it functions. Okay, how do we design the DSAT protection circuit and how it functions? Right? So yeah, so just give me a minute. I'll just have some water. Yeah. So okay. So do you want me to discuss some theoretical problems, or should we see what is desat protection? Like, what would you prefer? Like, I can explain about desaturation scheme, desat protection, or we can see some problems like theoretical only, all of them. So what would you prefer? Should we see about desat or should we see problems? Like, any preference for you guys? Anandi and Selva Kumar, any preferences?
We see about saturate desets.
Desat scheme, okay. Is it fine, Selva Kumar? Okay, we'll just see some desat scheme, okay? Okay, so you would have studied that there are different fault mechanisms, or particularly over here, overcurrent fault mechanisms that can occur in a half-bridge circuit, right? So two of these are illustrated over here. That is, you can have a direct shoot through failure if the pulses for devices 1 and devices 2, the top and bottom device, coincide. Then there is going to be a direct short across the DC bus, and that would shoot up the current to a very, very high level. Okay, the current would go really high. Or the other might be due to load inductor saturation, right? That is because the inductor current has increased too much, that is, the load current has increased too much, and the devices may not be rated for that much current. Okay. So in either case, what would happen is that the current device is going to carry a huge amount of current that may result in direct device failure or failure over repeated cycles, right? Due to over a period of time, the device may gradually it may deteriorate, and there is going to be device failure. Okay. And another thing is there is something called device derating. As temperature increases, the current carrying capability of the device decreases, right? So most probably, like, even if you see this device, yeah, they tell 24 amperes at 100 degree, right? At 100 degree, it is 24 amperes. At, at 25 degree, it may be even more. The current rating would be higher. Let's say it may be around 40 amperes or 50 amperes. And at, let's say, 150 degree, it may be less than 24 amperes, right? So this is called device derating, right? So it's called device derating. You go and look into any data sheet, you'll be seeing a device derating. Right? So again, as temperature increases, the current carrying capability decreases. Okay. So anyway, so what would happen is if the device would heat up, and because of it carrying more current, and obviously the device gets derated, that is, the current rating decreases, and the current would breach the limit. Okay, you don't want that. So there are a number of protection schemes. One is directly based on, you can sense the device current, but sensing the device current is a challenging part. There are a number of methods as to how you would do that, but what people generally use nowadays is called desaturation or current protection scheme. Okay, so let's see how it can be done, right? So why the name desaturation? Let's try to understand that. So we will go back to the output characteristics. You can stop me at any point if you're not understanding, but so let's go back to the output characteristics, right? So you have VDS over here, and you have your IDS, right? And you will be having your cutoff region, right? And then you will be having your ohmic region. I'm just drawing a rough graph, okay? So not exactly to scale or something. And then you will be having your saturation region. Okay. So the term desaturation came because it was initially used for IGBTs, but you understand that just generically, if we talk about, right, this particular region on the left side, right? The device is completely turned on, completely on, right? And on the right hand side, if you see, the device is behaving like a current source, right? The device behaves like a current source. So if you recall, what are the output characteristics of an IGBT, right? You would remember that IGBT is between the x-axis is the collector to emitter voltage and y-axis is the collector current, and you would be seeing something like this, right? Again, you will want to operate somewhere over here, right? Do you agree? That is, you would want to operate somewhere over here and not somewhere over here. You don't want to operate here. Okay. In an IGBT, you call this region, the blue colored region, as the saturation region. Correct. And this particular region, that is the flat region, is called linear region. Okay. So you will ideally operate it over here only in the saturation region. Why? Because you see that in the saturation region, right, in this region, VC is small. Okay, VCE is small. That is, in saturation region, VCE is small. Correct? VCE is small. Therefore, what is the drop across the device? Drop across the device, drop across the IGBT is going to be what? VCE into IC. Correct? If you can recall your IGBT. This is your IGBT. So this is VCE. Correct. So this is your collector, emitter, and then gate. Okay, so drop across the IGBT is going to be VCE into IC, and ideally you would want VCE to be small. VCE should be small, correct? So if you want something like this, you will want to operate it over here in the saturation region. Okay, now let's say there is a fault that happens. Okay, so I think it should take um, another graph over here. Probably it is very big, but still we will spend some time and we will try to understand. Okay, is it fine? Like, can we spend time? uh, since I have started, I want to explain it completely, right, so that the concept is clear. So you have VCE over here, you have IC over here. You know that initially there will be a drop. What is this drop? What is this drop in an IGBT? Okay, so what is this drop in an IGBT? Can anyone tell what is this drop? Okay, so you try to find out. So over here you see this is for increasing values of VGE, gate emitter voltage, correct? So you see again that there are three distinct regions. So one is cutoff region, right? The other one is basically this particular region, right? Right. So this particular region, correct? So this region is called the saturation region, right? And then finally you will have this region where it is almost constant. Okay, so this particular region is called linear region, right? So linear region, and then you have the saturation region. You have saturation region, right? And then you have cutoff region. Okay. So ideally, you will be wanting to operate it in the saturation region, correct? So this is where you want to operate the device. Why? Because in saturation region, you see that you are lying over here, right? In saturation region between this point to somewhere over here. Okay, so let's say you're somewhere over here. You lie over here. Okay. And let me name this. Let's say this is 10 amperes, this is 20 amperes, this is 30 amperes, and so on. Okay, let's say we have taken a 40 ampere rated IGBT or 30 ampere rated, whatever it is. Okay, so this is your saturation region. We want to operate it in the saturation region. Now, let's say there is a fault, right? Let's say there is a shoot through failure, something like this. Okay, and let's say the IGBT is operating at 800 volts. There is a shoot through failure, right? So what do you expect the current to be? The current will be very, very large, right? That means that we are no longer talking about 10 and 20 amperes. The current may increase to 100 amperes or even beyond. Okay. So, but over here you see that what is happening beyond 30 amperes, it kind of goes into linear region, right? IGBT goes into linear region beyond at 30 amperes, something like this. Okay. Right? So at 30 amperes or something, it goes into a linear region. So what would happen is that because right now the device has tried to go to very large current, so it would try to trace a curve something like this. Beyond this, okay, beyond this, it would increase, just go on increasing. Okay, the current has went on increasing. So what would happen is your VC is no longer limited to this point, your VC would also increase, right? Because basically the graph is something like this. Okay, so let's say you're over here, so the particular VCE would be over here. The VC is very, very large. Normally your VC is over here, right? But right now, due to a fault, your current has increased so much that the corresponding VCE point is also too high. Okay, do you get this? That means that you are no longer in the proper saturation region. So this is what we defined as a saturation region. We are no longer in the saturation region. Rather, you have your So we are no longer in the saturation region. We are going beyond the saturation region. Okay, that is you're entering into what is called as a desaturation region. You are no longer in the saturation region. You're trying to go to the linear region. Okay, so that is why this scheme is called desat protection scheme. So when there is a shoot through failure that's happening and the current increases so much that you're no longer within the nominal values of VCE. Okay, that is you go into the desaturation region, right? That is you try to go beyond the saturation region. That is VCE is too high. If your VCE is too high, what will happen? The loss is going to be what? VCE into IC. First of all, am I there? Okay. So the loss is going to be VCE into IC. VCE has increased so much, IC is so much, so the loss will be very, very high. So there will be heating. And finally, the power device will blow away. Okay, power device is gone. So do you understand what is desaturation? That is, you are no longer in this realm. You have already gone to a very high value of current. Therefore, you are no longer in the VCE range. Okay, normal VCE range. You have gone beyond this VCE range. So you can call these areas in the linear region or they are in the desaturation region. Okay. That is why this scheme is called DSAT scheme. And the same scheme is applied for MOSFETs as well. And the name is same, DSAT protection scheme. Okay. In MOSFET, actually the nomenclature is somewhat different. So that is why people can get confused, but it came initially for IGBTs. Anyway, so in a MOSFET, you know that this region is called ohmic region, and this region is your saturation region. People may think, oh, this is desaturation. Why is called desaturation? Actually, in MOSFET, if you see, you will be entering the saturation region, correct? If you apply the same principle to MOSFET at a higher current, when a fault occurs, you will be entering the saturation region. But in IGBT, same principle, you go away from the saturation region, just the name is different. Okay, so either way, you understand that you're no longer in these regions, you're going towards this region. You're going towards this region, right? Right? You're going towards this region. And in a MOSFET as well, you can understand what is the drop. VDS would be equal to I into RDS. Correct? For a fixed RDS value, if I increases due to a shoot-through effect, if there is a direct shot, right, then what would happen? Your I would increase. If there is a direct shot, your I would increase. Correct? Current increases, your voltage drop. I into RDS increases, I voltage drop increases, therefore the loss increases, and again heating happens. Okay. So this is your this is the problem. So we have just defined what is a problem, and we just understood what is desaturation region, right, from the output characteristic. Okay. So I hope till this point it is fine, right? Is it fine till this point? What is desaturation scheme? I mean, what is desaturation? Okay. Yeah, so the recording is going on good. Sorry. Okay, so how do we take care of this, right? So you understand that in both cases, either in a MOSFET or an IGBT, the VDS for MOSFET or VCE is increasing. So VDS increases or VCE increases in case of overcurrent. Okay, or during a short circuit. In both cases, VDS increases. So the underlying principle should be that you have a comparator. You have a comparator. You compare it with a reference value. Okay, you compare it with a reference value, and let's say this is directly measured from the device. V measured, and let's say this is the V reference. Okay, if V measured goes more than V reference, right, then the comparator will go logic high. Comparator will go logic high. And else, in normal operation, if we measured, if the voltage across the device that you measure is less than V reference, then comparator, okay, it is logic. Comparator will go logic high. So comparator will be at logic low. Okay. So this is simple, right? So this should be the principle. That is, you measure the voltage, you compare it with a reference. Over here, we were telling that normally this would be the maximum VCE. If the VCE drop goes beyond this, then you understand there is an overcurrent. For MOSFET, it is even more straightforward. You know what is I into RDS. RDS is fixed for a device. Let's say RDS for the device is somewhere around 16 milliohms. Okay. Right. So if we take some number also, it will be easier. So let's say the RDS is for simplicity 10 milliohms. Okay. The device can carry, let's say the device is rated for 50 amperes current. Okay. If the device carries 50 amperes current, then VDS is what? VDS is how much? 50 amperes into 10 millivolts. Correct? Or 500 so 500 millivolts. So 500 millivolts or 0.5 volts, right? Let's say due to short circuit failure, 100 ampere current is flowing. So VDS in that case would be equal to 1 volt. So since VDS has increased beyond the reference, a reference, let's say, is maximum current is 50 ampere. So you will set corresponding to that. If the VDS increases beyond that, then obviously the comparator has to go logic high, right? It has to go logic high. So if it goes logic high, you can couple it with the gate driver, or you can have a mechanism that, let's say, your the comparator goes logic high. So then in that case, I will disable my gate driver. Okay. You understand, right? So let's say you have an AND gate. Okay, you will have an AND gate over here. So this is the microcontroller pulses, and let's say this is the output from the comparator, which is okay. So which is given through a NOT gate. Okay, comparator. Can you understand the working of this circuit? So even if the microcontroller pulses are coming, if the comparator goes high, if the comparator goes high due to a fault, then output of the NOT gate will go low, right? If the output of NOT gate goes low, there is an AND gate over here. If the output of the comparator goes low, anyway, it would go low as well, irrespective of whether I'm getting pulses over here or not. Even if I'm getting pulses like this, if the comparator output goes high, output of NOT gate goes low, and therefore the output of the AND gate would go low, right? This can be given to the gate driver, right? And under normal operation, you know that the output of NOT gate will be logic high, therefore microcontroller pulses will come as it is under normal operation. Till this point, is it fine? That is, we have a comparator mechanism. The output of comparator is fed to an AND gate. Okay, AND gate between the microcontroller pulses and the output of comparator not fed. That is after a NOT gate. So till this point, is the logic clear? Both Anandi and Selva Kumar. If this is fine, we can go ahead.
Yes, sir.
Yes, sir.
Okay. So we just have an AND gate that will multiply my microcontroller pulses. Till this point, it is logical, right? We compare it with a reference value, measured value, right? And then output of comparator is noted, then fed to an AND gate. The AND gate will kind of multiply your microcontroller pulses with your comparator output. If your comparator output is logic high, then output of NOT gate is logic low. So irrespective of whether you get pulses or not, that's the important point. So even though you may be getting pulses from microcontroller, your gate driver will make sure that the switch is turned off immediately. Okay, once the comparator goes high, then your gate driver will make sure the device is turned off, even though you may get pulses from microcontroller. That is the beauty of this solution, right? So it is not that you have to tell the microcontroller to turn off the pulses. No, microcontroller pulses may come, but still this AND gate over here will make sure that the device gets turned off. Okay. So till this point, I hope this is reasonable, right? Okay. So let's go into practical implementation, right? Okay, so let's take the device. So let's say I take a MOSFET. Okay, so the MOSFET is connected to the power ground. Okay, so I will measure what is the potential over here. So the potential over here will be VDS, right? So that's your drain and this is your source. So I will measure the potential over here, and as I was mentioning, we will give this to a comparator circuit. Okay, plus minus, and I mentioned that here you will give the reference value, right? Again, you understand that the reference value should be with respect to power ground. Let me call this as let's call this as V reference. Okay, you will compare it with the reference value corresponding to the DSAT where the point where the transition happens. Let's call this as V reference. So this will be V reference, maximum allowable, right? Or VD set. Some people call this as VD set. Whatever it is, this is a reference value. Okay. So you compare with a reference value. And then what you did, you kind of knot it, right? You knot it and then you give it to an AND gate. So this will be the microcontroller pulses. Right? So this is the this is kind of handed, and then this is actually fed to the gate driver IC. So all of these things are later on. So I'll just remove these. But till this point, I hope this is clear. Okay. So why can't we have this kind of an implementation? Like, do you find any flaw over here? Is there something that is kind of that might pose a problem in normal circuit operation? Remember that the circuit is not just this device. So there would be a top device, right? And there would be a voltage source, correct? So this is your half bridge. So this is how your half bridge looks like. So, and you know that alternatively devices Q1 and Q2 are going to be switching alternatively, right? Q1 will be turned on for some time, then there will be a dead time, then Q2 will be turned on. Something like this would happen. So now you tell me, now that you know Q2 will turn on and turn off. This is VDC. So Q2 will turn on and turn off. So with this information, can you tell, will there be any problem, or is there something that is off over here, like something that we don't want? Okay, so you try to understand when you take the scenario. Oh, what happened? Oh. So you take the scenario when Q1 is on and Q2 is off, right? Q1 is on and Q2 is off. So during this period, what is VDS? In our case, what is VDS? Q1 is on and Q2 is off. What is VDS? Hello? Selva Kumar, so I'm not able to hear you. Like, can you type? Sorry? Okay, so Selva Kumar, I'm not able to hear you. You can type, I feel. I'm not able to get your voice. Okay, so you understand that during this period, VDS would be equal to VDC, right? So when Q1 is on and when Q2 is off. So at that time, what the comparator would see is a very high voltage, right? Let's say VDC is around 800 volts, correct? So at that time, the comparator is going to see a very, very high voltage over here, which is 800 volts. The comparator would get damaged immediately. These are all ICs, op amps, 5 volts operating voltage or something like that, correct? So at that time, what might happen is the comparator would get damaged, right? So you don't want that. So you want to ensure that when Q2 is off, right, when the device is off, the entire DC link voltage doesn't come here, right? There should be some mechanism that ensures that the entire DC link voltage doesn't come. Okay, so that is why what people came up is they came up with a very good idea that, okay, so instead of having a direct connection, right? Oh, what happened? Oh, I'm not able to rub it. Okay, so instead of having a direct connection, let me have a diode over here. Okay, let me have a diode. Okay. So now what would happen when the device is blocking 800 volts, right? When the device is blocking VDC, this diode will be reverse biased, right? So during this period, when VDS equal to VDC, let me call this as D, or let's call this as with some other D sat. This is the diode name. So when VDS equal to VDC, the diode D sat will be reverse biased. Diode D sat will be reverse biased. Okay. So this is how we are actually blocking. We are making sure that the comparator doesn't get damaged. We have a diode over here. Okay. Right. So this is the first step in the design, that you have a diode. So what should be the voltage rating of the diode? Can you tell what should be the voltage rating of the diode? Anandi and Selvakumar, you can type, like, if you are not able to unmute. What should be the voltage rating? How much should the diode be rated?
More than VDC, sir.
Sorry.
Sir, more than VDC.
Correct. So it should be rated for more than VDC. So just hang on a second. I will just computer kind of fell down. So as you told, the diode should compulsorily be rated for more than VDC. The diode should be rated for more than VDC minimum. That's a prerequisite. So this is the first step. That is, you add a diode that will block 800 volts. I mean, you make sure that your comparator is fine. Right. Now it presents another problem. Right. So this is during turn off. When the device is turned on, right? When the device is turned on, that is when Q1 is off and Q2 is on. When the device is turned on, at that time VDS would be simply I into RDS, correct? Which is also a positive number, which is also a positive value, I into RDS, that is appearing over here, correct? So at that time, we need to make sure that the diode, we need to make sure that DSAT is forward bias. Only then we can sense what is the current, right? Or we can give it to the comparator, right? We need to make sure during this time that DSAT, the diode DSAT should be forward biased, correct? Should be forward biased. I hope you understand, right? Like, okay, we added the diode to isolate it, the high voltage side, but point is when during normal operation of the device, when the device turns on, that time we want this circuit to operate, right? So we want this particular circuit to operate. So for that, we need to make sure whatever is the VDS over here, that should be coming over here. That is, the diode should be forward biased, right? So that is the next challenge people started working on. How do we make sure that diode DSAT is forward biased? How? How do we make sure? Okay, right? So I hope you understand till this point. Okay, we added a diode. Now diode is blocking the high voltage. How do we make sure that the diode gets forward biased during normal operation of the device? Because ultimately that is the aim. I want to have VDS over here. So I want to have VDS over here. Okay. Okay. So let me take a new slide, and people came up with a very novel circuit topology, right? So let me redraw this. So till this point, we have seen that from here, there is going to be a diode, right? Which will block the high voltage. And then I'm intentionally drawing this longer. So we give it to a comparator, and then we take the NOT of it, and then we give it to an AND gate. microcontroller pulse, and this is to gate driver. And we saw that it is compared with the reference value. Okay. Now the idea is to make sure diode DSAT turns on when the switch is on, when Q2 is on. When Q2 is on, the DSAT should be forward biased. Okay, right. So what people came up with is, okay, so what people came up with is they kind of had a current source over here at this point. Okay, let me call this as I charge. Okay, ICSG. They had a current source over here. Okay, first I will explain you the topology and then we can see it's working. Okay, so they had a current source over here, right? And yeah, so they had a current source. This is connected to VDD, right? So they had a current source over here, and yeah, so they had a current source over here, and then you have a capacitor connected directly across. Okay, so they had a capacitor connected over here. So now you tell me there is a DC current source, right? And then there is a capacitor. Let me call this capacitor as CBLK. I will tell you what is BLK later, but we have a capacitor. So what we did, we added a current source and a capacitor, right? And okay, so you tell me when the capacitor, when you have something like this, there is a current source and a capacitor, then what would happen to the capacitor? The capacitor would go on getting charged, right? So this capacitor will go on getting charged. Okay, fine. So till this point, I hope this is fine. And what people did was they added, um, so they added a MOSFET over. Okay, so let me draw with a different style. Okay. So they added NMOS over here. This is also a MOSFET only. So this is also NMOS, this is also NMOS. Just that this is a power MOSFET and this is a signal level MOSFET. Okay. So they added a NMOS over here and they made sure that this NMOS is getting pulses from microcontroller. Okay. So let me take a new slide. So you have the MOSFET over here, and then we added a diode. Okay. So what people did was they added a resistor over here. Okay. And as I was mentioning, there was a capacitor. Okay. And there was a current source over here. Okay. Current source over here. And finally, there was a signal level MOSFET. There was a signal level MOSFET. Okay. Okay. So this is your actual VDS point. So this is your VDS, and then this is DD sat. Okay, let me call this as RBLK. This is CBLK. Okay, and this is given to plus, and this is minus. Okay, so what people thought was, this is Q2. When Q2 is off, right? When Q2 is off, then what would be the circuit? So when Q2 is off, then we just learned that, okay, so Q2 is off, right? So the entire voltage that comes over here is VDC. And then the diode is going to be reverse biased, right? The diode is going to be reverse biased. So you have VDC coming over here, correct? Diode will be reverse biased, right? And then there's your resistor in the circuit. There is your current source, and there is your capacitor, and then there is a signal level MOS. Now what I will do is I will turn on the signal level MOS. Okay, when Q is off, when the Q2 is off, what I will do is I will turn on the signal level MOS. Okay, so now that this MOSFET is turned on, so what would happen is the current source would find a path through this. Okay, current source would find a path through the signal level MOS. Okay, so do you understand till now? So till now what has happened? Q2 is off, Q2 is off, and the diode is blocking entire VDC. So the diode is blocking the entire VDC. There is R over here and there is a C over here. The current source would find a path through the NMOS. Okay, so this is your NMOS. This is just a MOSFET. Okay, so in this scenario, what is the voltage across this capacitor? Can you tell? So Q2 is off. This is the first mode of operation. Q2 is off, right? At that time, diode is blocking entire DC bus voltage, right? And there is the current source over here. And we are telling that since we will turn on this MOSFET, we will turn on this MOSFET, okay, when Q2 is off. So when this MOSFET is turned on, then the current source find a path through this MOSFET. So what is the voltage across the capacitor? What is this voltage? Can you tell?
VC, sir. VC, sir. Is it correct?
Sorry?
VC.
VCC.
So just don't think about all those things. See, this MOSFET is turned on, right? So basically this MOSFET is kind of shorted, right? So now I'm asking you, what is this particular voltage? What is the voltage between this to this? This MOSFET is turned on directly. Now you tell me what is the voltage.
VCC.
So you're telling this is VCC. This VCC.
Yeah.
See, but you understand that if I tell that this is a current source, right? So what is a current source? What can be a current source? So the current, so you imagine that the current source is something like an inductor, right? So inductor doesn't allow current to change instantaneously. You assume that it's an inductor. Okay. So now the point is, you understand that there is current source over here. Okay. So the same current is flowing through this MOSFET as well. Okay. So the MOSFET is kind of shorted, right? The MOSFET is kind of shorted. So this potential and this potential are kind of same. Okay. So I can conclude that this voltage will be the same as this voltage. So this voltage is going to be same as 0. Okay, because NMOS is turned on now, right? So I will turn on NMOS and I will make sure that this voltage is 0, right? Because the NMOS is turned on simply. Okay, the current source just finds a path through NMOS. That's it. Okay, so it is like you take your buck converter now once again. So let's say you take the buck converter. Sorry, correct. And then you have an inductor, right? So the point is, see over here, if you turn on this device, correct? So this is your load voltage V naught. Okay. I turned on this device. Even if you turn on this device, this voltage is going to be 0, right? This voltage would be V naught. This voltage would be 0. This is V naught. Similarly, over here, you see this device is going to be turned on. So if this device is turned on, what is the voltage at this potential? This is going to be same as ground voltage, right? This is the same as ground voltage. Okay. So this voltage is 0, V plus. Understood, both of you? Is it fine?
Yes, sir.
So your NMOS is turned on. So you see that a switch is turning on. When the switch is turned on, it's like a short. So the voltage is same as this voltage, that is ground voltage, 0 volts. So when Q2 is turned off, what I did, I turned on this NMOS, this particular NMOS. So then the current source find a path through the NMOS. So V plus is equal to 0, correct? And V minus is V reference. Oh, what happened, man? Yeah. So V minus same as V reference. So what will be the comparator output? Comparator output would be low, right? Comparator output would be low. Okay. So there is no fault that is being sensed now. Agreed? So there is no fault as such. Q2 is also turned off. I have just turned on this NMOS. So then what happened was V plus is going to be 0 because the NMOS is turned on, and V reference is coming as it is to V minus. So V plus is less than V minus. V plus is less than V minus. Therefore, comparator gives logic low. Right? Agreed till this point? Is it fine for both of you? Can we go to the on condition?
Sir, one doubt. This
Yeah, please.
NMOS, the microcontroller pulse, is it the same pulse of that AND gate? AND gate one
So NMOS, what kind of pulse should the NMOS get? Should it come from, should it be the same as pulse for Q2 or should it be
different.
huh? Yeah,
That is my doubt.
so how different should it be? Like what should be the pulse? It should be complementary, right? Correct? So what you should be getting is something like this. Correct? If this is your microcontroller pulse, you will knot it and then give. Right? Do you get it? When the device, when Q2 is turned off, I want the NMOS to be turned on. So Q2 is off, I want NMOS to be turned on. So when Q2 is turned off, I want NMOS on. So I will feed pulse of Q1 to NMOS, right? I can feed the pulse of Q1. Do you agree? I can give pulse of Q1 over here because Q1 is a complementary device. Q1 is a complementary device. Do you understand? Selva Kumar?
Sir, little no.
Okay.
So
So
Q1 pulse, you are telling the pulse of Q1 can be used for NMOS for switching on. Same pulse.
correct. Correct. Because why we are seeing that NMOS provides a path for this I charge. For this I charge. So NMOS is just providing a path. Okay. So I'm turning on NMOS when Q2 is off. When Q2 is in the off condition, Q2 is in the off condition, I am providing a path for I charge that is happening through the NMOS. So basically, I want NMOS to be turned on when Q2 is turned off. When the power device is turned off, I want NMOS to be turned on. Okay, and vice versa will happen. So that is why I will give the pulse of Q1 to NMOS. Okay, I will give the pulse of the complementary device. Is it fine, Selva Kumar?
Okay, understood. Sir.
Okay, fine. So till this point, I hope this is fine. Now let's see the main thing, that is when the device is on. Okay, so when the device is on, I can approximate the device as a resistance, like this is RDS. Okay, so this is Q2 is on. So when Q2 is on, normally, naturally, right? So this is RDS. There is a current I flowing over here, ID. So I'm sensing the voltage, right? There is a diode over here. We told there is a resistance. Okay. Probably I should bring it down. Yeah. So there is a resistance, and then there is I charge. Okay. There is a capacitor over here. Now this NMOS is not getting any pulse. Okay, because Q2 is turned on, I am noting the Q2 pulse. Okay, so when Q2 is turned on, NMOS does not get any pulse. So this NMOS is out of the picture. Okay, so um, let's go back. So over here, you will then feed it to the. Is it fine for both of you? NMOS is now out of the picture. Okay, I will not give any pulse to NMOS. Is it fine? I have approximated the device as RDS on because it's in the ohmic region. Let's assume this is not natural operation, no overcurrent and all. Okay.
Okay.
So during that, when NMOS is turned on, what should be the current path for I charge? I charge will go something like this. Correct? Through this resistor. Okay. Right? Is it fine? Both of you, Anandi and Selva Ganesh, Selva Kumar.
Yes, sir. But same
Okay.
current.
Yeah, it's a current source, na? So the current source will have a fixed current. Okay. And we are all talking about very small current sources. This is few milliamps. It will not change ID by too much. Your, let's say ID is 20 amperes or something. This is few milliamps. There will be no change in your power current. Okay. In that case, you try to understand what is V plus. Can you tell me what is V plus? Let's say this is the forward voltage of the diode. Okay, this is RBLK. So what is V plus now? Can you tell? Can you tell what is V plus? V plus will be simply I charge into RBLK, right? Plus, just write KCL plus VF plus, let's call this as VDS plus VDS. Do you agree?
Yes, sir.
Anandi, do you agree? Like, is this fine?
Yes, sir.
Okay. So this is your V plus that is going to the comparator. So when the device is turned on, I'm getting the V plus voltages I charge into RBLK plus VF plus VDS. What is V minus? This is simply V reference, right? V reference. So when would the comparator turn on? So the comparator would turn on if V plus more than V minus, comparator would turn on. That is, this indicates fault, right? So you just solve this inequality. I charge into RBLK plus VF plus VDS. If it goes more than V reference, then it indicates that there is a fault. Okay. From this, you can get what is VDS, right? You can get what is VDS, right? So if VDS is more than V reference minus I charge RBLK minus VF. If your VDS, if the device voltage goes more than this particular value, then the comparator would turn on. Agreed? VDS is nothing but I into RDS. So you know what is RDS. If I increases more than this, so I into RDS, if it goes more than this particular value, then it indicates a fault. Okay, then the comparator would turn on. Is this fine? Do you understand how the comparator action is happening? Basically, V plus will be more than V minus, and you know the current source will be flowing something like this. So this is your forward voltage drop for the diode, right? So you write what is V plus, I charge into RBLK plus VF plus VDS. Okay. So if VDS increases beyond this particular inequality, VREF minus VF minus I charge into RBLK, then obviously it indicates a fault, comparator would turn on. Is this fine, both of you?
Yes, sir. Yes, sir.
Okay. So, oh, it is already 8:43. I'm sorry, like I did not see the time. I think we are way past time. Like,
This industry was
Sir,
closed.
huh?
sir, when
Really,
Q2 is off,
Huh? When Q2 is off,
so in this condition, V plus is 0. So
V
V
plus is 0.
reference is a negative value. So V plus is greater
No, V
than V.
reference is a fixed value. See. V reference is fixed. I was telling now. V reference is fixed based on the output characteristic. So V reference is already fixed for the device. So I know that, see, let's say V reference is somewhere around 10 volts. If my VCE goes more than 10 volts, I know there is a fault. Okay. If I was just telling now, so this is 10 volts, let's say. If high
Okay.
current flows, you will be somewhere over here. So your
Okay.
VCE is much higher than 10 volt. So this is your V reference. So if your
Okay.
VCE goes more than 10 volts, then obviously then the comparator would turn on. So as I was telling, this V reference is a fixed value. What is changing is this particular value. Okay.
Okay.
So now you can understand, right? If V plus is 0 is less than 10 volts or whatever is the V reference. It may be 9 volt, I think, for commercial gateways. I forgot the exact value, but whatever it is, you understand that it is 0. So comparator doesn't function, like it doesn't give a fault signal. You understand now?
Okay, sir. Yeah, understand.
Okay. And I don't know, for some reason the ink got erased, but so is this fine till this point? Like V plus, what is happening during normal turn on? So I charge will find a path through this. And yeah, so is this fine till this point? Like, I think we should stop here. Is this fine? I will tell you
Yes.
why we are having this capacitor in the next week. Okay, we will see this in the next week. But till this point, is it fine?
It is for noise suppression or in addition to something else also there is this C plan.
Correct. So this is basically for, yeah, like I will tell you during the next week. So point is like there is one particular you should consider when the device is turning on, just turning on. Okay. So initially it was blocking 800 volt. Now the device turned on. So when it turns on, the device voltage will fall from 800 volt towards zero. Okay. So during this period, I don't want this to false trigger. Okay, I will explain the next class. Like
Okay, sir. Okay, sir. Okay, sir.
till this point, my throat is also paining a little now, so we can probably stop over here. But do you have any doubts during the normal operation?
No, sir. This good session. I have clear understood. Actually, little bit doubt was there in the desaturation points, so I got clear.
Okay.
Thank you, sir.
Okay. So if this is fine, I think we will conclude over here. And just one more point, if you were wondering how you will realize a constant current source, right? I charge is a constant current source. I hope you would have studied in analog circuits. There is something called as a current mirror circuit. Have you guys read about current mirrors, current mirror circuit? Or they are basically just BJT or CMOS amplifiers. You would have studied about BJTs, right? So BJTs, you can have them in different configurations. BJT is a current controlled current source, CCCS, current controlled current source, IC equal to beta times IB. So I will just supply a small base current, I can get a good amount of IC, right? So that is the principle used over here. That is how you get a constant current source. But anyway, this is just some extra information. We will continue with the DSAT protection and why this capacitor is used from the next class. We'll just quickly recapitulate this DSAT scheme and then we will continue from why capacitor is required. But till this point, is it fine? Like both of you?
Okay, sir.
Yes, sir.
Okay. Okay. So I think we will stop over here. And thanks to both of you for staying for such a long time and listening to the
Thank you.
session. But yeah, have a great week. So if it is fine, like, can you just tell like whether you guys are doing BTech, MTech, or PhD or something?
I am going for PhD, sir.
Where?
I am going for PhD, sir. Applied. So,
Oh, okay,
part
okay,
of
nice, nice, very good.
power converters. I am working as scientist in DRDO.
Oh, okay, okay, fine, fine, fine.
So
Great.
my PhD part of coursework, I am learning this power gap device. That wideband gap, how it is working. Actually, we are using gallium
Okay,
nitride
so
device.
you're in which institute?
Center for Airborne System, Bangalore, sir.
Oh, okay, okay, nice, nice, great.
We are using many places now nowadays gallium nitride device. So that's why
Yeah,
I
right.
selected this course over this wideband gap.
Okay, okay, great.
Thank you, sir.
And Anandi, like you're also doing masters or something?
Yes, sir. Just now, yeah, I'm applied for PhD, sir. Just
Oh, great. Sorry?
yeah, just applied for the PhD, not college starts
Okay,
for
okay,
full
great,
time,
great, great.
and
Super,
in
super.
Chennai, sir, Anna University.
Oh, in Chennai, great, okay. நானும் actually தமிழ் தான். நான் BTech I did it from, oh wait, I'll just stop recording.